Good afternoon, everyone. My name is Constantine. I am a RF engineer in Alba Orbital, and I am going to give a brief overview of our technology. So the satellites we've been fabricating here at Alba, what do they do? I'll talk a little bit about their specs and give some mission ideas. So, the overview, I'm just going to briefly introduce Alba Orbital for those who are not familiar or very familiar with the company, talk a bit about our goal and why we scale down and we fly, then go into our technical overview. Excuse me. I'm going to talk I'm going to talk a little bit about the first satellite, Unicorn 1, and then go to Unicorn 2, and mention a little bit what we can do with our guidance system and what our payload capabilities are, and then also present to you, the pocketqube orbital deployer, the Albapod as we call it, and mention a little bit briefly what our ground station is composed of. Finally, I'll finish with some mission ideas and some potential collaborations that can be done with Alba Orbital for these satellites. So pretty much our mission statement hasn't changed since last year. This slide is, I admit, from last year's workshop, because the mission statement has not changed. We want to advance the pocket because we want to grow the community and we want to make pocketqubes matter or great again. So why scale down? I think that is pretty much obvious, so I'm not going to spend too much time on this. So you have satellites that go to up to 2-3 tons. We are below the kilogram, and being more compact, so having a smaller miniature satellite is less expensive to fly. There's less junk in space, and also we can make bigger satellite constellations. So Alba Orbital has gone down this path of the miniature satellites of the pocketqubes, along with all the people here in the community. So who are we? We are a small company in Glasgow with 12 full-time staff and growing. We are working from parts to full platforms, and we have already flown 2 Alba Orbital satellites in December 2019 for an inter-satellite link test, plus our customer's satellite, because we're not only flying our own satellite, but also other people's. So 6 in total in orbit, and we'll be flying again at the end of this year 2 Alba Orbital satellites, a Unicorn 1 and a Unicorn 2, plus again the customer satellite, both recurring and new customers. So that being said, I'm now going to give you a technical overview of what our satellites are. So what you're seeing here is Unicorn 1, or rather a CAD of it. This is the first version of the satellite that is going to fly at the end of the year. We flew last year our improved version, and we couldn't fly Unicorn 1, so we still need to fly this one. So we're flying it at the end of this year. This is a 2P pocketqube, 50 by 50 by approximately 13 centimeters, 5 by 5 by approximately 13 centimeters. It has 270 approximately grams. It has a mass of 269 grams approximately, and you have more than 100 grams available for payload. We have a 1 watt on orbit average power, and this satellite also has a passive attitude stabilization. It is compatible obviously with the PQ60 standard, and it is the basis of what we now call Unicorn 2. So from Unicorn 1 to Unicorn 2, the size has changed. We moved from a 2P to a 3P, and last year, as I said, we flew 2 of these satellites, 2 unicorns, and this year we'll be flying another 2 with some improvements made between the 2 versions of Unicorn 2. So what I'm going to present next is pretty much the improvements. I'm going to show a technical overview of the improvements that have been made on the Unicorn 2 satellite from Unicorn 1 to Unicorn So as I said, Unicorn 1 is a 2P satellite. Unicorn 2 is a 3P satellite. So you can see here on the left and on the right, the two versions. On the left, you have what we call Unicorn 2.0, which is the 3P pocketqube that flew last year in December 2019. And on the right is 2.1, which will fly at the end of this year. Now, before going into the differences of the two unicorns, I'm going to talk about the similarities first. So in both cases, we have kept an active attitude stabilization. So we have an active ADCS. We have switchable lines from Unicorn 1 and Unicorn 2.0 and Unicorn 2.1. We kept this as well as the options for available protocols. We generate a lot more power, up to 10 watts on orbit and 19 watt peak. 90 watts, not something I wanna generate right now. So the platform mass has increased a bit. We have a bit more, again, than 100 grams of available payload. The main difference, between Unicorn 2 and Unicorn 2.1, the form factor remains the same, both for the wings, the way they deploy, the body, and what is inside the satellite. We still have our guidance system, our sun sensors, our patch antennas, and our monopoles. They deploy exactly the same way. The fundamental difference is what I'm going to show here. So basically what you see here is the cut of the insides of the satellite. In this case, you're seeing the 2.0 version, which is the satellite that has an aluminum body. So the fundamental difference and major improvement between the two satellites is the body. So as you can see in the pictures here, on the left is Unicorn 2.0 again, which has an aluminum body, and on the right is the Unicorn 2.1, the one that is flying at the end of this year, which has a different kind of body. So that is the main difference, major fundamental difference that allowed us to improve this satellite. Why this? Because in the first case, on the left, we have an aluminum body. On the right, we have a body made out of wind form, which is a carbon fiber material mixed metal. I don't have the exact composition for that, but it's a more lightweight material that allowed us to improve not only our payload bay volume, but also our harnessing techniques, as well as our payload volume. It's also a material that is very thermally inert and therefore can be exposed. Takes a lot of time to have its temperature changed, which is good in our case because it provides by itself some sort of first thermal control. So I am going to mention here that, so basically I'm going to talk a bit about our guidance system and the payload capability. So on the top left, you see basically a schematic of the new body of Unicorn 2.1, the one flying at the end of the year. The payload bay is where basically you see the optical payload standing in, and you can see that if you can replace basically this optical payload with some payload boards that we have designed that you can see there. The numbers are not very clear there, but basically, like I said, this new material, we have re-optimized the chassis, so the body of the satellite, and we have variable size payloads that can go there. You can actually stack up to 4 or even 5 boards of the ones, and probably the ones I have here and the ones you can see in the presentation. These boards can go from 95 to 102 millimeters of length by 46, which is the other side of chassis. They are easily removable, way more easily removable than the first version of Unicorn 2, so version 2.0, and that makes it also easier to test. So that being said, I also want to talk a bit about our guidance system. Our guidance system hasn't changed drastically since last year. We still have a system that it has 2-axis sun sensors and has 5 degrees of pointing accuracy. It has its reaction modes and its magnetorders. And I have to say here that among all the subsystems, the guidance system is the one that requires the most power. So because a lot of it is made from brass, it can heat up very easily. So wind form being a material that is thermally inert is actually quite useful because we can actually use the wind form as some sort of heat vent. Yes. So having talked about the payload and the guidance system of the latest version of our satellite, and we've actually flown last year 2 satellites for an inter-satellite mission, and this year we're flying another one, Unicorn 2A and Unicorn 1, the Unicorn 2 for an Earth observation mission. I would just like to finish this by giving 2 things. First of all, talking a bit about our deployer. So the way we deploy the satellites in space, some of you already know this, is with our Albapod, the pocketqube orbital deployer. So this pod can take up to 6 1Ps or any combination of 2 or 3Ps that adds up to 6 1Ps. It has a base that is made of aluminum, and the shell, its casing, is of the same material as the satellite. It's the windform shell. So this pod, which also we used last year, right, is actually quite lightweight, and it has been tested to meet NASA standards for random vibration. So this year we'll be flying so our 2 satellites and our customer satellites in 2 of these pods, and we'll be flying a LEO mission at 520 or 525 kilometers. It's 505. We will be using UHF and S-band channels to do respectively telemetry and downlink our image, because we're flying an optical payload to be able to take images of the Earth. So we've also made a mobile ground station that has a UHF and an S-band channel. The UHF channel is used for uplink and downlink, mostly for telemetry and tracking and commands. And the S-band is a downlink channel only that will be used to downlink the images we've taken. And we will be having our mobile station moving around, not too much, hopefully, not too much. So for this to work, we have equipped our ground station for the UHF link with a Yagi antenna that is around 14-15 dpi, circularly polarized. And our satellite at the moment has a monopole of -1 dpi. At UHF 401, 402 megahertz, that is quite a compact antenna. So the gain you can get from a compact antenna FR4 substrates is not always the best. So this can be improved, but for now we have enough margin in our link to be able to accept -1 dpi of gain for the UHF antenna of the satellite. For the S-band link, our satellite we've made a circularly polarized patch with 5 degrees of gain, DPIC, excuse me, and in this case, the patch has a half power bandwidth of 60 degrees. With that being said, we have a product that we ourselves have used for client's intersatellite link mission. And this year we'll be flying our own mission to test the satellite's Earth observation capabilities. So already we have a relatively low cost technology for commercial applications. As soon as you start putting in constellations, you can carry even more commercial applications, such as Earth observation, which is something I think people want as soon as they have like agricultural or maritime economies or more. Actually, I'm taking two things that concern me because I'm Greek, so I know these two things are of interest. And then you have things like RF sensing missions, which is something our clients do. And because this is the pocket cubes as well as the CubeSats, let's be honest, are originally a tool that was developed for education. We are also very interested in R&D collaborations, for example, trying to integrate propulsion system, mini propulsion systems or deployable lenses, and we are actually working actively on trying to integrate some transparent antennas, flat transparent antennas on our solar panels, but for higher bands such as X or even X band. I'm not going to say K band. I would like to, but not. So the pocketqube platform is a platform that is a low-cost technology that can be used for multiple missions and has potential for improvement through R&D collaborations even more. And this is something we are actively seeking both new missions and new people to these missions with, as well as any collaborations that will improve the performance of this platform to people like this. That's it for my presentation. Thank you very much. If you have any questions, please let me know.